Hi everyone, my name is Negar Saeidi. I'm a specialist engineer in ventilation with Vale Base Metal North Atlantic Project Group. For today's presentation, what I've put together is a case of a relatively small yet impactful ventilation changeover that we did at one of our mines in Sudbury, Ontario, Creighton Mine, about 2 years ago. We used Ventsim DESIGN to validate the concept for this changeover, pinpoint critical stages for commissioning and critical areas of the mine in terms of airflow distribution prior and post to this changeover. But before I get to the details of this ventilation changeover case, I want to walk us all through a refresher slide about criticality of ventilation for our underground mine operations. So we obviously need ventilation as a business to create a safe work environment for people as well as equipment underground. But as you saw earlier this morning in Cheryl's presentation, we know that ventilation accounts for 50 to 80% of our typical mine's energy expenditure. As remote operations grow, such as our Voisey Bay operation within Vale, and our mines get deeper, such as our Coleman mine, as well as Creighton, which is the case of discussion today, the energy demand for ventilation, as well as cooling and heating of the air increases. So operating costs of our mine increases. And then in such condition, it is critical to have an effective management strategy for our mine ventilation air to be able to have a safe and profitable operation. So with that in mind, I'm going to walk you through a brief introduction to our Creighton Mine ventilation system. Here's a schematic of our ventilation system. The current capacity of our mine is about 1.8 million CFM, equivalent to 850 cubic meter per second. Surface air goes through a caved zone, which is from old mining area, currently acting as a natural heat exchange area for the mine, conditioning the ventilation air. Air goes through this NHEA area via three sets of intake fans on 1420 level, 2300 level, and 26, highlighted in red circles, in series with two sets of booster fans on 5400 level and 5000 level. They all are in feet, just making sure we're on the same page. And then all the air entering the mine is collected on 7200 level, from there going down to deeper parts of the mine. Currently at Creighton, we are on 8500 level deep, and our studies are looking at 9500 level and even deeper. So as we are done mining in the upper country, we preferably start looking into opportunities to reduce airflow to those levels that we're done, or close them down, to be able to redirect the air to deeper parts of the mine where we are actually operating. And that was basically the basis of this ventilation changeover that we went through. So what we were dealing with was we wanted to redirect about 150 kCFM of air from an old mining area, which is about 4,000 to 5,000 level, an old mining zone, and redirect it to deeper levels below 7,400 level where mining is actually happening. The assessment process we went through had three key steps. We started with looking at the infrastructure requirement. We looked at existing raises and drifts, what's their use, what's their size, what's their capacity in terms of velocity and resistance. Can we use this existing infrastructure, or do we need to put new ones? We looked at our existing fans. Do they create enough differential pressure to allow moving this volume of air to deeper parts of the mine, or do we need to upgrade them? Do we need more power? And ventilation controls, where do we need to add a wall, a louver, any adjustments, etc. And then we looked at implication of this change to our life of mine plan. As I said, we are looking at 9,500 level and even deeper in the future. So is this in line with those production targets? as well as looking at old mining area, like these levels that we are pulling air from, what do we have left there? Are we going to ever go back and do mining? Do we have some key infrastructure such as electrical substations, backfill stations? I don't know. Is this the main emergency exhaust path for the mine? Just verifying those requirements throughout the mine. And all these two steps were done with a lot of ventilation modeling, as well as calculations hand in hand to see if we can use the infrastructure and if it meets life of mine plan. And with that information, we simply did a project cost versus benefit. How much does it cost us to make this changeover, and what we get afterwards in terms of new mining fronts, improve air quality, and enhance safety measures in our working area. And then it comes to actually how to commission this change, like what are the sequences of the event to ensure that this change has minimal interruption to the existing mine system. So as I said, it was about 150 kCFM of air from 4,000 to 5,000 level. What we had in terms of existing infrastructure was our number 9 shaft, directing all this air down to 6,800 level, which is the bottom of our cage currently, and then 6,800 is used as main commute for our mining personnel, as well as people working at a snow lab, which get access to 6,800 level here. So we have velocity limits for this area, and it's currently out of capacity, so we really couldn't send more air. Then we had to start looking at other options on how to make this diversion, redirect this air from those levels to the bottom of the mine. What was done at the time, working with mine design people and geotechnical people, we found a new location was found. I didn't find a location, so I was not part of the team at the time, but a new location was found working with mine design and geotechnical people to put in a new raise, connecting 6,400 and 6,600 level, using these two levels as air transfer drifts for the air coming from old mining area, and directed to 7,200 level, which is the collection area, and then from there, sending the air down to the bottom of the mine. So again, ventilation modeling and calculations, we came up with two 150 horsepower fans on each of these levels working in series, and we showed that this arrangement would make no changes to the main mine fan performances. So at this stage was a lot of back and forth between ventilation modeling, like Ventsim design use, versus what we think would actually happen in the mine based on experience and what our calculations showed, what actions we needed to take, and what was the stages of commissioning. So what I've put together for the next few slides is 3 examples of what actually Ventsim showed us, what actions we took, and what we actually saw in the field. So first one is that the model showed us once we commissioned the 2 fans, the 64 and 60, the 2 sets of fan, a total of 4 fans, on 64 and 66, and redirect the air from the old mining area, it would cause a leakage on the top levels so we're closing down these areas, right, to pull from down. It causes a leakage towards our 11 shaft main exhaust raise on 3,800 level, 200 kCFM. So we believed it. What we planned was to adjust the louver accordingly. This is part of mine's emergency access, so we had to maintain a minimum velocity, and that was 30 kCFM. And that's actually what we saw in the field the day that we were commissioning. We did the measurements. We saw relatively the same amount of leakage on that level, and we adjusted the louver, and the issue was resolved. The second thing we observed was that once commissioning the fans, 6,400 and 6,600 level, the model showed us that we would see increased pressure across an airlock door that we had by the booster station on 5,000 level. We were hesitant about what we were seeing in the model, especially because we knew our model is not well reflecting the area as it is in the field. So what we thought was like, let's wait and see what actually happens, and if we need to get the construction crew involved to change that door or make it, I don't know, add another airlock door to it or find a way around it. And as expected, that was not what we saw in the field. We had a damaged door there, and it was having a little bit of a leakage, about 15 kCFM. And an example that we didn't have right information in the model, and we didn't get reliable results out of the modeling. The last one is the fan performances that we were seeing from our model for the both series of fans that we added to the system. Once we had it commissioned, the pressure sensors we had installed by the fan stations were showing a different number than what we expected in the model. We followed up with a handheld reading, and we realized our sensors were damaged. So again, we had another source of reliable information from our model and the calculations to work against verifying the issue with our sensor installation, and that was addressed as well. So a few conclusion points here. I think we all agree that Ventsim is a good tool for simulating and analyzing our underground mine ventilation systems. But this is another way of saying, and a statement that was repeated a couple of times throughout the day, garbage in, garbage out. So our model's accuracy heavily relies on the quality of the information that we put in. What we practice within Vale, and I'm sure other companies do the same, is that we always rely on first principles and fundamental laws of ventilation. So every time we do a ventilation modeling using Ventsim, we go back, verify it with actual manual calculations. Does it make sense? Is it correct or not? So I highly recommend that, because in that way, you would know if you really can rely on your model, if it is reasonable, if you can use it to predict behaviors or not. And of course, calibration is not a one-time thing. It's a continuous act. You have to continuously collect data, have your database updated, and compare what you see in the model against what you see in the field, add more information. All the PQ surveys were measured throughout the day, can be used in the old mining areas especially, that are for life of mine infrastructure. And again, keep your field data up to date. It was mentioned earlier that we usually have brief sample of data that we don't use properly. It's important to collect data systematically, make sure measurements are accurately done, the conditions are captured accurately, so you can use it in the right manner. And the two last points were repeated one way or another throughout the day. Blindly accepting simulation result is quite dangerous. Ventsim is an easy tool to use. It's very user-friendly, and makes everybody feel comfortable and confident to do ventilation modeling. But actually, you require some expertise with mining background as well as ventilation knowledge to be able to understand what comes out of it is reliable or not. So I think that's a message that all the presentations conveyed today. Be careful when you use such a useful tool. It can be dangerous at the same time that it can be very useful for our design in the future. So that's all I had for presentation today. If there are any questions, I'd be happy to answer. Thank you for your attention.
Thank you, Negar. Do we have any questions for Negar? Yeah.
Thank you. A great presentation. Just a quick question there. I was curious to, you're mentioning that you're always validating before, running the Ventsim, you're validating with hand calculation. Do you just do a simple model, or how does it, what's the process?
Yes, we do a multiple scenarios, depending on what we're doing. We do simple scenarios of basically sketching a couple of lines and representing a ventilation network and do that calculation that way. Also, we have our ventilation guidelines that we're currently in the process of updating for Ventsim, and that has literally examples of like for shock losses, friction factors, for inputs we put for auxiliary ventilation and main fans. Those are very, very basic, simple calculations that we create a ventilation model for it with Ventsim, and then have an Excel file on the side to compare the results. Yeah.
Okay, thank you.
Thanks, Hugo. Any other questions? Yeah, I think this is a good demonstration of how I think one of the side effects of having a model that you're critical of and maintaining is that you can often, a side effect of that is you catch out things like bad sensors or maybe some sort of blockage that's come up that you're not aware of. It's a good demonstration of it. Yeah. Okay, if there aren't any more questions, I'll just thank Negar once again.